So in this video we're going to go over the second partials test for relative extrema. So just like there's a second derivative test for functions of one variable, there's a second partial derivatives test for functions of two variables. And the second partials test can be used when the gradient of the function you're working with is equal to 0 at a critical point, x naught, y naught. And remember, the gradient of f is just a vector formed by the partial derivatives of f. So if we're saying that the gradient is equal to 0, that's telling us that the partial derivatives are equal to 0 at a critical point x naught, y naught. So we could also just have said, suppose the partial derivative of x is equal to 0 and the partial derivative of y is equal to 0 at a point x naught, y naught. So the second derivative test says take the product of the second partial derivative with respect to x times the second partial derivative with respect to y minus the square of the mixed partial. And remember, f sub xy and f sub yx are the same, so we could just as easily have put f sub yx here. So we take the product of the second partials minus the square of the mixed partial, and then you go through and you analyze these different scenarios. Is this calculation that's called the discriminant, is this calculation right here greater than 0? If it is the second partial with respect to x positive or negative? And then that helps you to determine whether you have a local minimum or a local maximum. Is the discriminant negative and the second partial with respect to x positive, then you have a saddle. And if the discriminant equals 0, then the test is inconclusive and you have to try some other means to figure out whether you have a relative min or max. The saddle point here that we're talking about right here looks like this. This is a saddle. So a saddle is a place where it's possible to have the derivative with respect to x equal to 0, the derivative with respect to y equal to 0, but the graph in one direction is concave up, but concave down in the other. So like a mountain pass, locally both a low point and a high point at the same time, so a saddle. So example, it says locate and classify the critical points for f of xy equals 3x squared minus y cubed minus 6xy. So first we need to find the critical points. So to find the critical points, we take the derivatives, the partial derivatives, and then we set them equal to 0, or we look to see where they're undefined. So the partial derivative with respect to x is going to be 6x minus 6y, because we hold y as a constant with respect to x. And the partial derivative with respect to y, this will be 0 because x is treated as a constant, so we'll get minus 3y squared, and then minus 6x from here. And then what we need to do is set these equal to 0. So we set 6x minus 6y equal to 0, and we set minus 3y squared minus 6x also equal to 0. And then I want to notice if I add 6x to each side here, I get 3y squared equals 6x. And if I add 6y to both sides here, I get 6x equals 6y. So that tells me that by the transitive property of equality, for the two equations here to be simultaneously equal to 0, I need negative 3y squared to equal 6y. If I add 3y squared to both sides, we'll get 0 equals 6y plus 3y squared. And this can be factored as a 3y times 2 plus y. Distribute to check your work. 3y times 2 is 6y, 3y times y is 3y squared. And then we can use the zero product property to find out the values of y that work. So when we look at this, we see y equals 0. We'll zero this side out. and y equal -2 would zero this side out. And then we just need to step over to one of our two equations here and figure out what the value of x is that goes with the value of y. So here I have the relation 6x equals 6y, which tells me that x equals y if we divide both sides by 6. So if x equals y, that means when y is 0, x is 0, and when y is -2, x is -2. So our critical points are going to be the points 0, 0, and the point -2, -2. And if we needed to check our work, we could just plug these points into our partial derivatives and make sure that they actually zero out the partial derivatives, because by claiming they're critical points, we're saying they simultaneously make those partial derivatives zero. We don't have any undefined places for the partial derivatives, so we won't get any critical points that way. So once we find the critical points, we will use the second derivatives test, or the second, in fact, better would be to say the second partials test, because this test involves the second partial derivatives of our function of two variables. So I think a better name is partials. So we'll run our second partials test. So to run the second partials test, looks like I erased part of my derivative. The derivative here, the derivative with respect to y had a -6x sitting in it. So to do the second mixed partials, I need the second derivative with respect to x of my function f, which means take the derivative of the partial derivative with respect to x. So we take the derivative of the derivative, so f sub xx, the second partial with respect to x, is just going to be 6 from here. And using this, I can calculate the second partial with respect, first with respect to x, then with respect to y. Looking at this, it's going to be a -6. And here I have my first partial derivative with respect to y, so I can calculate my second partial derivative with respect to y. And taking the derivative with respect to y is going to give me -6 times y. So now I have the pieces that I need to create the discriminant. So the discriminant as a function of x and y is going to equal, we take the product of the second partials with respect to x and y. So f sub xx times f sub yy, we get 6 times -6y is -36y, and then it's minus the square of the mixed partial. So when we square -6, we get 36. So here's our discriminant. And then what we do is use the discriminant to test our critical points. So we calculate the discriminant at 0, 0, which is going to equal, when we plug in y equal to 0 here, we're going to get 0 minus 36 is -36. So we look up at the test scenarios, and this says right here, if the discriminant is negative, which it is, and the second partial derivative with respect to x is positive, which it is, we have a 6 for that, and here we have a -36, then we're told that we have a saddle point going on. So we've got a saddle point like we had here in this picture. So that tells me that 0, 0 corresponds to a saddle point, so it's neither a local minimum or a local maximum. Now we can run the discriminant test, or the second partials test, on the point -2, -2. So when we do that, we get -36 times y, but y is -2, minus 36. So we get a negative times a negative is a positive. This is going to be 2 times 36 minus 136. So 2 36s minus 136 is just going to leave us with 136. So now when I look at the discriminant test, the second partials test applied to the critical point -2, -2, I see that the discriminant is positive. So we're in one of these two situations. So the discriminant's positive. And then here I look and I say, hey, the second mixed partial, which is 6, is also positive. So if the discriminant is greater than 0, which it is, and the second mixed partial with respect to x is greater than 0, which it is, then our point corresponds to a local minimum. So we have f of -2, -2 corresponding to a local minimum. And of course, if we wanted to know the local minimum value, we would just plug the point -2, -2 into our function to find out what that local minimum value is.